Hey everybody, welcome back. I hope everybody had a good spring break. I hope everyone is okay. This is definitely very strange times we live in right now. I just want to make sure that everyone's well. This is going to be the first of our, whatever this is, lectures. Um, I've done this before. If you've seen any of my YouTube videos, this is exactly how I do this. I have a lecture set up where I can write with Smartboard software and a graphics tablet, and it's worked so well, but I don't know if this process works for everybody. So it's not exactly the same thing as sitting in the class and listening to me, but I hope if you have questions, you ask them. But anyways, we're going to pick up where we left off. Last time we talked about the first three sections of this. We looked at the wave nature of light. So we figured out how to mathematically describe how light behaves, and that's something that scientists love to do. We talked about a little bit about quantum theory and why hydrogen atoms give off light. If you take a hydrogen atom and you excite it by throwing in lots of electricity at it, it will give off light. And the reason it does that is because electrons will jump from where they are at the nucleus. They will jump farther away to a higher shell. And when they drop back down, they have to release the energy they absorbed, and they release it in the form of light. And we know that this light is, I can't draw this right now. I'm sorry. Let me redraw that. Scientists draw this light as a photon, so they draw it as a particle with like a little wave inside it. But this photon has a specific energy that is quantized. So photons can't have any energy they want, and they have an energy equal to E equals h nu for frequency, Planck's constant times frequency. So this is how much energy a photon can have. It totally depends on its frequency, but it can't have any energy that it wants. Okay, good. So today we're going to talk about, well, if light can act like a wave, maybe matter can act like a wave. So the first couple things we're going to do here are going to be a little bit mathematical, a little bit strange, and this is why I broke this chapter up into two sections, just because it's a huge amount of stuff to get done in one night. Anyways, we're going to pick up here talking about the wave nature of matter. Yes, the wave nature of matter. So a long time ago, a scientist named de Broglie comes along and says, well, if light is quantized, if light can't have any energy at once, maybe matter can behave exactly the same way. So let me show you a picture. De Broglie, if you've ever seen a musical instrument before, you know that musical instruments have standing waves. It's the same thing as, if you've seen this experiment before, we have two people like with a rope. There's one person there with one person there, and they start waving the rope up and down, and all of a sudden they get the rope to go up and then down. And then if they do this a little bit faster, if they wave the rope up and down faster, they get a standing wave up and a down. That's what's trying to be shown here. If they wave it faster, they get three standing waves, and so on. So de Broglie realized, well, maybe an electron orbiting an atom can do exactly the same thing. So if I take it, instead of this whole thing right here, let's kind of swap this out and go to a little bit bigger picture. Let's imagine this is the nucleus of an atom right in the middle, and instead of an electron literally revolving around it, maybe we can mathematically describe the electron as if it was a wave. Because if an electron was a wave, all the electron has to do to make it all the way around here. Imagine taking a standing wave like this, up, down, up, down, up, down. But instead, take the ends and bring the ends together until they meet. So this is a standing wave that basically repeats itself over and over again. And he's like, wow, if I can do this, I can say that matter acts like a waves. And de Broglie realizes that not any standing waves will work, only standing waves that have a whole numbers of wavelengths, right? So something with 3.5 wouldn't work. So de Broglie does this and comes up with a very famous equation, which basically says, wait for it, here it is, that we can describe lambda, lambda's our equation for wavelength, lambda, a wavelength for matter. Now this equation is h is Planck's constant, m is the mass of a particle, and u, and I hate when scientists do that, they change variables up on it, u is velocity. Now, if you've taken physics in a while, the product of mass and velocity is something called momentum. So momentum is often abbreviated as, I don't know why, but scientists use P to abbreviate momentum. P equals m times v. And everybody knows what momentum is. Would you rather get hit by a fly moving 30 miles an hour or a baseball moving 30 miles an hour? Everyone chooses to fly because the thing that hits you isn't just the velocity, it's the mass multiplied times the velocity. The baseball hurts a lot more than the fly does. It has more momentum. So this equation is often written as lambda equals Planck's constant divided by p, or momentum. But it's a really cool thing. This equation does not work for things like Volvos and frogs and baseballs. But the smaller things get, in science, the smaller things get, approaching the size of an atom or smaller. All right, what's smaller than an atom, a proton, a neutron, or an electron? When you get down into this size range, the normal rules that we have for physics start to break down, and we need a new set of rules. So we call these quantum rules. All right. So if you have something, an atom is really small. If you know the mass of an atom and you know how fast it's moving, you could describe its wavelength. And if you can describe the wavelength of that, you can describe the wavelength of a proton, the wavelength of a neutron, the wavelength of an electron. It's an amazing thing. So de Broglie is able to predict that a neutron or an electron could act as if they have a wavelength. And if something can have a wavelength, then you can invent some technology for this. So this is a pretty amazing thing. Whoop, where's my voice recorder? Let me pause it for a second. So here's a hypothetical problem. Imagine you've got a 25-gram bullet moving at 612 meters per second. And you want to find out, well, what's the wavelength of a bullet traveling 612 meters per second? Well, let's plop it into de Broglie's equation. So if you want to find the wavelength of a bullet, wavelength lambda equals Planck's constant, which is 6.63 times 10 to the negative 34, divided by the mass, 25, times 612. Oops, I forgot to put the 6 in there, 612. Now, whatever 25 times 612 is, it's going to be still huge. The product of these two things is going to be huge compared to Planck's constant. So this is like taking a tiny number dividing by the small number. You don't end up with a big number here. You're going to end up with a wavelength that is tiny at the result. So I'm just going to say tiny. But we can still get the math and solve our problem. So if you plug the numbers in, you end up with a wavelength of 4.3 times 10 to the negative 38 meters, which is so small. It's actually smaller than an atom. Just to put this in perspective, an atom, a hydrogen atom, has a diameter. A hydrogen atom has a diameter. I don't know where that came from. The diameter of a hydrogen atom from here to here is about 1 times 10 to the negative 10 meters. So the wavelength of a bullet traveling 612 meters per second is a tiny, tiny, tiny fraction of the size of a hydrogen atom, which basically means it's meaningless. Well, the way to make this equation kind of work in our favor to get a larger number here is to make the things on the bottom a whole lot smaller. So what if we resolve the problem? What if we had something completely different? So what if you have something like electron? By the way, it dawned on me in the previous problem that I did not convert the mass of the bullet into kilograms, which I should have, which would change my answer by just a couple decimal places, but that's okay. If you did the same problem now, you end up with wavelength equals Planck's constant 6.63 times 10 to the negative 34. Wait for it. Wait for it. Let's make sure my recorder is on. Yes, I am on. And then this number is going to be divided by the mass, 9.11 times 10 to the negative 31. That is the mass of an electron, multiplied by its velocity. 63 meters per second is about 120 miles an hour. Okay, so now you got an entirely different problem because you have a small number on the top and a small number on the bottom, so you might end up with a number that's a little bit different. So let's calculate it. So when we do the calculation now, we end up with a much more realistic wavelength, 1.2 times 10 to the negative 5 meters. So the cool thing about this is if you can make an electron act like a wave, then you can make the electron do things that light normally does, like make microscopes out of it. If you want to make a microscope, what you need to do is, you've seen a microscope before. You have basically a tube like this with a lens here and a lens there, and you got a sample down here in a pad, and let's say the sample is some kind of amoeba or whatever. You have to have a flashlight down below to shine light up through the sample to go here, because your eye is going to be right here looking at the bug, right? So why not do something very similar? We're going to reverse this. We're going to take instead an electron gun and fire electrons through an electromagnetic lens. So instead of having a glass lens, we're going to have an objective lens here that is a magnet, and it is going to focus our electrons down onto a sample. And now the electrons are going to bounce off the sample and head towards a detector, which allows us to say, hey, we know exactly where these electrons came from. And that allows us to see images of the same amoeba in very close up, or flies or cells or whatever, or even atoms. We have microscopes that allows us to see atoms, but they operate because we make electrons act like waves. So it's a pretty cool deal, right? Making electron waves is a win-win for everybody. And there's all kinds of scientific equipment you could do. Like you can get electrons to diffract, right? You can use electron diffraction, which is a pretty weird thing. Well, I'm not going to talk about the concept of diffraction right now, but get the idea that making, if an electron could act like a wave, it's a pretty cool thing. Okay, now let's move on to some more weird things about science. Okay, so now we're going to go a little bit weird. When we're talking about things that are very small, and when I say small, I don't mean like bugs um, um, or grass. I mean things like electrons or protons, neutrons, atoms. The rules change, and we specifically have a rule which comes from finding things, or finding out how fast things are moving, which is known as the uncertainty principle. We're going to talk about that just in a minute, and then we're going to get to the Schrodinger equation, and we're basically going to come up with a new method of describing where electrons are in an atom. All right, so wait for it. Here we go. Okay, so if if um, if electrons and protons and neutrons can act like waves because they're small, we're trying to locate subatomic particles, we kind of have a problem with it. And this is what's known as the Heisenberg uncertainty principle. So what we know from the uncertainty principle is it's impossible to simultaneously know two things: momentum and position. Now momentum is really velocity. Momentum is an equation which is mass times velocity. So what this equation is really saying is it's impossible to know where the position the particle is, and how fast it's going at exactly the same time. I can know one or I can know the other, but I can't know both simultaneously. And you end up with this really strange equation. Delta x is what's known as the uncertainty in position. It's basically like if you were trying to find imagine this, going on top of a bridge and taking a rock and dropping the rock onto a target below. How big would you have to make the target before you were sure that every rock hit, right? So here's a hypothetical. You've got a target and you're dropping rocks from a height. How big does this target have to be so that every time you drop it, the rock always makes it somewhere inside that target? This diameter of this circle is what we're talking about here. It is the uncertainty in position. Obviously, you have to find a bridge that it's safe to drop rocks off, but it's a separate question. You can imagine doing this with playing darts. How big would the dartboard have to be such that every dart you threw at the wall hit the dartboard? And for me, it would be a dartboard that would cover like most of the side of my house. But anyways, I digress on that one. So when we're talking about subatomic particles, we can either know where they are or we can know how fast they're moving, but we can't know both at the same time. So delta x, uncertainty in position, multiplied by delta p, the uncertainty in momentum. And because momentum is p equals mv, the mass of an object isn't really going to change. So what is going to change is its velocity. So this is really uncertainty in velocity. It has to be greater than or equal to Planck's constant divided by 4 pi. So the best way to talk about this is to actually put it into use. Use this equation to solve a problem. All right? Let me pause for a second. Okay, so here's our hypothetical. So we know that electrons in hydrogen atoms are known to have a velocity about this big. Now this is really fast. 5 times 10 to the 6 meters per second is 5 million meters per second, plus or minus 1%. So that's how fast electrons are moving inside the hydrogen atom as they act like a wave or a particle at the same time. So what we want to do is find the uncertainty in position. How uncertain, or how big is, remember our analogy to, here's our bridge that we're standing on, and we're dropping rocks onto the ground below. How big does this target have to be such that every rock dropped hits somewhere inside this space, right? So right now, what we're saying is we kind of know how fast the rocks are falling, right? What we're not sure right now is what's the error in, or the uncertainty in knowing where they're going to land, all right? So let's look at a couple specifics about the hydrogen atom. So we're going to say, whoops, I'm going to get rid of all that. Sorry. We know the velocity of an electron is about 5 times 10 to the 6 meters per second. And so we want to use the uncertainty principle equation. So we know that delta x, uncertainty position, multiplied by delta p, uncertainty in momentum, is got to be greater than or equal to h over 4 pi. Well, what we're trying to solve for right now, we know the velocity. Oh, we also know the mass. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. So we know this term right here. We're trying to solve for uncertainty in position, so let's do a little bit of algebra. We're going to divide this both sides of the equation by delta p, and that's going to give us an equation that allows us to solve for delta x. Delta x is greater than or equal to, where are we? H. And if I'm dividing both sides by delta p, I've got 4 times pi times delta p down here in the denominator. All right, so let's break this out. I'm going to move the whole thing over here. So delta x, uncertainty position, is equal to Planck's constant, 6.63 times 10 to the negative 34, divided by 4 pi. And if you don't have a pi button in your calculator, just use 3.1416 times the uncertainty and momentum. Momentum is just mass times velocity, so I'm just going to multiply these two terms together. Mass is 9.11 times 10 to the negative 31 times 5 times 10 to the 6. All right, apologize for my sloppy handwriting. So now you got to use EE button when you're solving this, or somehow to get the correct answer, all right? Because there's a lot of scientific notation going on. Okay, so let me pause while I get a solution for this. Whoops, this isn't equal, it's greater than or equal to. All right, so let me pause. Pause. Okay, so when you do the math, and I rounded this answer a little bit, we end up with an uncertainty in position greater than or equal to 1 times 10 to the negative 9 meters. So literally, if we're dropping rocks, that's how big our target is. Oh, that's a terrible circle. How did I even do that? I need a better circle. I can do better. So I'm trying to draw a circle on a ground on a graphics tablet. So we're dropping rocks on this. This is how big the circle is. Now, what does this number actually mean? Right? Well, we're talking about hydrogen atom, and it might be important to kind of talk about, well, how big is a hydrogen atom in the first place? And a hydrogen atom has a diameter, that's the distance from here to here, of about 1 times 10 to the negative 10 meters. Well, exactly how big is this number compared to this number? Which number is bigger? 1 times 10 to the negative 10 and 1 times 10 to the negative 9. Obviously, this number is bigger. By how much? By a factor of 10. So the diameter of the hydrogen atom, the entire hydrogen atom would fit in here, right? And by the way, inside here is where the electron is supposed to be. Let's kind of shade this in. The electron is supposed to be in here, but our uncertainty in where its position is actually greater than the size of the entire atom. So our uncertainty is equal to essentially this entire little circle we've drawn here, but the hydrogen atom is this little bit itself. Okay, so this is kind of an idea of how the uncertainty principle works, right? This is why we can only know one thing really well at a time about an atom. Okay, so let's talk about some more weird things about the atom. A next really important person to come along in the 1900s was a person named Erwin Schrödinger. And Schrödinger was a physicist who basically was thinking about the atom and realized that this wave stuff about atoms is kind of really important. So basically had to come up with an equation to describe the wave nature of matter. So de Broglie equation essentially isn't good enough. Schrödinger's trying to he's using really advanced calculus way beyond the scope of this course. And he's trying to say, I have an equation. We know that matter right now can either be act like, I think I just said be act like. Please forgive my grammar. Matter can either act like a particle or it can act like a wave. Particle or a wave, depending on the circumstances. So Schrödinger, I just said his name wrong. Schrödinger is going to come up with an equation which has both of these natures in it combined. And so the name of his equation, he's going to come up with some kind of equation called a wave function. And this is the fancy Greek letter psi. A wave function which mathematically describes the particle and wave nature of matter at exactly the same time. Okay, so what does he come up with? The wave function itself, I haven't drawn a psi in a long time, but there it is. This wave function, which describes the idea of matter acting like a wave at the same time it acts like a particle. It has no direct meaning itself, but what it does is this. It allows us the probability of finding an electron in a certain region around the electron. This is the most useful thing that the wave function does. It allows us to kind of figure out what's our chances of finding an electron here versus here around an atom. All right, so take a minute and we're going to kind of think about this. Here's a hypothetical. Imagine you have a 5-year-old child, and the 5-year-old child has just stepped in a bucket of paint. And you've also just given the 5-year-old child a puppy and espresso with chocolate and sugar. And what you're doing is trying to take a picture. You're going to take a picture of every single place the 5-year-old has been, let's say, over a minute. So you're going to take 1 picture a minute or 60 pictures. So what you're going to be left with is a set of footprints on the ground, 60 different footprints showing where the child has been during that time. Well, you can imagine the electron in a hydrogen atom as kind of being like the same thing. So here I am. I'm going to draw a hydrogen nucleus. So hydrogen nucleus is just a proton, and I want something else. I want another color. I want something else to draw my electrons. So what I want you to imagine I'm doing right now is you're trying to imagine taking a picture of where the electron has been for over a certain amount of time, right? So to do this, I am going to start drawing little dots in here, and each dot represents the place that the electron was in a specific moment of time. Now, if I was really good, I would be doing this completely randomly, but I'm not that good. And I did find a computer program that actually simulated this really well, but I haven't found that yet. So let me pause for a second. You don't want to see me drawing dots on a page. Okay, we're back. So the thing to think about this is, imagine we are taking a picture of all the places that the electron in a hydrogen atom has been over a certain amount of time. And what you're left with is something like looking like this. Now I can't draw in 3 dimensions, so obviously this is just 2 dimensions. So stop and think about this for a second. We're so used to thinking about an electron as a thing that orbits the nucleus of an atom. And as something that orbits the nucleus of an atom, I can just kind of wait for it. If the electron is here, I can just kind of wait for a certain amount of time and say, aha, it's going to be right here. But with this type of diagram, what we find out is that the electron has been in lots of places. So what we're looking at now is, I'm going to write down a word. probability. Where are we, if we're going to kind of take a step back in time, where are we most likely to have found an electron around a hydrogen atom? Or rather, what region are we most likely to find an electron in? If we had to like reach in blindly, where would we, if we had to pay 25 cents each time we wanted to reach in and grab a chance for grab an electron, where would you want to put your money? Where would you want to most likely grab the electron? Are we likely to find electrons in here, in this region inside? No, because it looks like there's at no time has any electron been in this region here around the nucleus. Are we likely to find electrons out here? Well, no, we're not as likely because I don't see any spots out here where the electron has been. Maybe there's been a couple times it's out here, but where do we have the highest probability chance? Where is the highest probability of chance of finding an electron around the atom? It's right in here. It's in this region somewhere around here that goes around the atom. Now, I can't draw a circle to save my life with this graphics tablet. Oh, that's just awful. Let me pause for a second. All right, I redrew the circles, but they're not that much better. So what we end up with is a region. I'm going to write the word region. We end up with a region around the atom where we are very likely to find an electron and regions where we're not. So guess what? Electrons don't orbit atoms. We know this now. Electrons do not orbit in very precise rings. Instead, they're just kind of likely to be found somewhere in a region around this nucleus. Now, if you took this region and extended it into 3 dimensions, what do you end up with? You end up with something that looks like a sphere. So the modern knowledge, this is what Schrodinger's equation gives us, is it allows us to predict a region around the atom where we're very likely to find a nucleus. And instead of using the term shell, this is not a shell anymore. This is, I mean, you would probably call this like a jelly donut with room in the middle for cream. But instead, the new term we use for this is what's called an orbital. So an orbital is a place where we have a high probability of finding an electron. So the way that Schrodinger describes this is the wave function for an atom allows us to find the distribution of electron density. I like that term because it's basically we find out that this region in the middle is where we're the most likely to find an electron. And essentially this is what I've tried to copy. And I do this on the board and people give me strange looks for about 5 minutes until I'm done drawing dots on the board. So get this. We're no longer interested in saying, aha, the electron is exactly right there and only right there. Instead, now all we care about is where are we most likely to find the electron around the atom, okay? So as it turns out, when you run through Schrodinger's wave equation, you end up with a lot of different types of these orbitals that mathematically come out. And we find orbitals that are spherical in nature. And again, this is a full 360-degree sphere. The nucleus is in the middle. We have a high likelihood, a high probability of finding electrons somewhere inside this region. This is like very familiar to people. People get this one. But when it comes to here, this is another type of orbital that's possible. So we have a high probability of finding the electrons somewhere in one of these 2 regions, but not anywhere else. And it gets even more complicated because we have a couple more different types of orbitals. We've got d orbitals and we've got f orbitals. And these are all, what I like to try to tell people is not to get bogged down in the crazy shapes, but just get the idea that these are mathematical regions that we have proven where we are very likely to find electrons around the atom. So what's the moral of the story here? Back in the day, you looked at models of the atom which had a nucleus and a shell and another shell and another shell, and we had places around the atom where we were likely to find electrons. The second shell would have held 8, and I'm not going to draw 8 in there. The third shell could hold 8. And what we find out is this knowledge, this was great for building models. This was great for teaching people chemistry. This Bohr model of the hydrogen atom was great for a long, long time, but we realize that it's technically not true anymore. Instead, electrons are found in orbitals. And the simplest type of orbital is basically just a sphere. And the next type of orbital has that dumbbell shape. And it's just different, right? Try not to get bogged down in how weird these things are. It's just different. This is what scientists have found actually happens in reality. All right, so just take a minute and pause. So what we found is out of all these different types of orbitals that exist, we end up with uh, rules for basically figuring out how electrons get packaged in orbitals. Just like we know that oxygen, when we find oxygen in nature, oxygen always comes packaged with two oxygen atoms bonded to each other. We have rules for figuring out if I have an atom with, like, let's say 20 electrons, where are all those 20 electrons going to go? Those 20 electrons are going to be found in very specific orbitals, starting from the inside of the atom and then working their way out. So what we're going to talk about next are rules for writing electron configurations. Configuration is just this. It is an order for how electrons are arranged inside an atom. So what scientists have found over time is there's 4 different types of orbitals. And each different type of orbital, scientists have given a letter name. And we have s orbitals, and s orbitals are spherical. P orbitals have this flower petal or dumbbell shape. D orbitals, I'm not even going to begin to describe what these are. These represent d orbitals, and these represent f orbitals. And if you remember your shell theory of the atom and how many electrons sit in each of these orbitals can hold a specific number of electrons. S orbitals can hold 2 electrons, p orbitals can hold 6, d orbitals 10 electrons, and f orbitals 14. So that's something to keep kind of tucked away in the back of your brain. How many electrons each of these orbitals can hold. So what we're going to talk about right now is if I had an atom with, let's say, 20 electrons in it, first of all, what one of these orbitals am I going to choose first? In what order? How do I do this? So the whole process of electron config is, I can't talk and write at the same time. Electron configuration, or electron config for short, is a process of organizing where each of these electrons are going to go in an atom. All right. So the rules for writing electron configurations are here. Electrons will reside in the lowest possible energy first. All right. And then we move up. Each orbital can accommodate a maximum of 2 electrons. And what that means is an s orbital can hold 2, but a p orbital, there's 3 different shapes for a p. There's one that goes that way, one that goes that way, and then one that goes that way. Each one of these types of a p orbital can hold 2 electrons. Before we said p's can hold 6. Here's all 6 of them. This term is not going to make any sense right now. Electrons will pair. We're going to talk about orbital or electron pairing in a bit. And then last, but orbitals will fill in the order indicated in the following figure. So let us go to the following figure. Here it is. This is the direction that orbitals get filled. And this is our start point up here. For any atom, we have to start from this specific orbital and then work our way on. So it basically, we go through 1s and we come back up here to 2s and the 2s to the 2p. And effectively, when you're done drawing in these loops, this is what it looks like, the game Candyland. So I call this process electron configuration Candyland. So every single atom, no matter what, has to start by putting electrons into the 1s orbital and then keep going with this. All right, so the best thing we could do right now is an example. So let's take an atom, a random atom. I'm going to take an atom with 20 electrons, and I want to put electrons in order in electron configuration. So I don't even need to know what this atom is. So I ask myself, I go back to the chart and I say, which orbital has to come first? The 1s orbital has to come first. So I'm going to write down the 1s orbital. And then we have to ask ourselves, how many electrons can you put into an s orbital? And the answer is 2. So the way I'm going to represent that is by putting it up here as an exponent. Now this is not an exponent, it's just the way we represent this. So what this is saying right now is I have my first s orbital, and that first s orbital has 2 electrons in it. So let me pause and write that down. So this is what this process means. The 1s means it's my first s orbital, 1s, first s. The 2 just means that this particular orbital has 2 electrons in it right now. Okay? So that's what all these things mean. Now we're going to keep going. So what did I use up? I had 20 electrons. I used up 2 of them. I have 18 electrons left. What's the next orbital available? If I go back to my chart, the next orbital available after the 1s, the 2s. So I'm going to write 2s. And then again, how many electrons can go into an s orbital? I'm going to put 2. So I had 18. I used up another 2. I have 16 left. What's the next orbital available? The next orbital available after the 2s is the 2p. And in a p orbital, I can put 6 electrons. So the 2p is next, and I can put 6 electrons in it. So I have 16, I used up 6, I have 10 left. What's after the 2p? Look on your chart. The next thing after the 2p is the 3s. And we know that s orbitals can hold 2 electrons, so I'm going to put 2 electrons in there. And now I have 8 electrons left. Well, after the 3s comes the 3p. And the p can hold 6 electrons, so I have to put 6 in there. And I have 2 electrons left. What's after the 3p is the 4s orbital, the 4th s orbital. And I know it can hold 2, so I'm going to put 2 in there, and I've used up all my electrons. And what you've written here is what's known as the electron configuration for this particular atom. This is exactly where all of its electrons are. So in a way, it's kind of like the old shell model of the atom. We start from closest to the nucleus here. So I'm not going to write anything. There's my proton, or my nucleus, proton plus neutrons. I can't write it. My nucleus is here. These are electrons closest to the nucleus, and I work my way out. All right, so it's a pretty interesting arrangement. If you have electrons left, you have to fill an orbital. I couldn't just go in here and put 1, and then put 5, and then put 3, and keep going. I would have to fill this all the way out. So let's do another example. Let's take an atom with, let's go the next atom up. Let's say we have an atom with 21 electrons. So I'm going to do exactly the same process. I'm going to start with the first orbital available, which is a 1s, and I have to fill it. I have to put 2 in there. Now I have 19 left. The next orbital available is a 2s, and I have to fill it. I have to put 2 electrons in there. 17 left. Then I go to a 2p, and I can put 6. If I've got 6, I have to fill it. Now I've got 11 left. After the 2p is the 3s, and I have to fill it. So now I have 9 electrons left. After the 3s is the 3p. I've got 6 electrons, more than 6 left. I have to fill it. Now I have 3 electrons left. I go to the next orbital available is the 4s, and I have to fill it. I have to put 2 in there. Now I have 1 electron left. Where does this electron go? The next orbital available right now after the 4s is not the 4p. It is the 3d, and I have 1 electron left. I'm going to put 1 electron in there. And now I'm done. I have none left. So in case you're getting confused, you know, it goes up 1, 2, 3, and then it goes to 4 and then 3. The reason for this jump, why we don't go directly to the 3D, has to do with energy. And the idea is the 4s orbital is at a lower energy than the 3d orbital is. So the way we're doing this is we're going from the lowest energy orbital all the way up to the highest energy orbitals, which is why the d gets filled after the 4s. So try not to get confused with this. So by the way, what's different? This is atom number 21. How is this different from the atom that came before it? Let me go back and quickly copy down the electron configuration for the atom before this. So if you look, there's not a whole lot that's different between the atom with 20 electrons and the atom with 21. In fact, the entire electron configuration that comes before it is exactly identical. The only thing different about this atom is it has this extra 3d1 electron. So you see this type of thing a lot. All right, so I want to show you real quick. People always ask, well, how do all these orbitals kind of stack together? I'm going to show you real quick. So orbitals end up stacking together. The first s orbital, the 1s orbital, is this orbital that's buried inside here that's gray. And then the 2s goes kind of stacks on top of it, and then the 2p. And the 2p has three parts. It has a part in the x direction, which is often written as 2px. And then, look at that, I totally screwed that up. Wait for it. It says this is the x direction. So this is the 2px, and we know the 2px can hold two electrons, and then there's the 2py. I don't know why they have the y up. This can hold two electrons, and then the 2pz. And all the orbitals end up stacking together. Now, it's completely beyond the scope of the class to make you draw something like this or predict it. The only type of question they would ask is, can you identify an s orbital versus a p orbital versus a d orbital type thing? But never ever make you kind of bring this whole together and draw it. All right, so take a minute. Okay, so what I've done here is drawn the electron configuration for the first 12 atoms, starting with hydrogen, helium. Hydrogen only has one electron, so its electron configuration is 1s1, then helium. Lithium comes along and fills the 1s and goes to the 2s, and so on, 2s2, 2s2, 2p1. So boron is the first atom that has a 2p1 electron. And then carbon, 2p2, 2p3, 2p4, 2p5, 2p6. So if you're looking, everything underneath is exactly the same. After neon, like a typewriter, I go back across to the left-hand side to sodium. Everything underneath here, if you look at everything underneath, from 1s2 to 2s2 to 2p6, that's exactly the same electron configuration as the neon atom is. So there is a shorthand way of writing the electron configuration for an atom. If I wanted to write the electron configuration for sodium in a shorthand way, I could say, well, all of this stuff here is basically neon. So we write neon in square brackets, and then we write what's new. What's new after neon is 3s1. For magnesium, look at this, same thing. 1s2, 2s2, 2p6, that's neon. So magnesium, I would write square brackets, neon, and then 3s2. Now, you can't get creative with this. Unfortunately, the way to do this is you could only do this by putting the noble gas that comes before it. So let's find something else where I have a noble gas. I come up here to helium. So I could write the electron configuration for lithium. Lithium, this part of lithium is basically helium, so I could say lithium, square brackets, helium, and then the other thing that's new is 1s2. Sorry, 1s, 2s, yeah, I screwed that up, 2s1, right? Lithium is helium and then 2s1. So unfortunately, you can't just write the atom that comes before it. This can only be done by putting the noble gases in here. Okay, so a couple things, right? I want you to focus on, let me erase some of the stuff that I just put up there, and we're going to focus on a couple things. So I want you to focus in a couple places. I want you to look at hydrogen. Let me change color. I want you to look at hydrogen. I want you to look at lithium. And then S1, S1. Who's the next one that's got an S1? Over here, sodium. And then I want you to look at the periodic table. And where are hydrogen, lithium, and sodium on the periodic table? Hold on, let me get a periodic table. Oh, there they are. Hydrogen, lithium, and sodium are all in exactly the same column or group on the periodic table. Hydrogen and everything in this group, as you're going to find out, ends in S1. Go back to beryllium and magnesium. Beryllium and magnesium end in S2. Where's our boron over here? Boron was P1, carbon was P2, P3, P4, P5, P6. So what you end up finding are patterns on the periodic table. And in fact, when you end up writing electron configurations for a whole bunch of atoms, we end up finding this. We end up finding that atoms that are in exactly the same group have exactly the same ending configuration. Everything over here, the first two groups on the periodic table are where s orbitals and only s orbitals are being filled. Lithium is 2s1, sodium is 3s1, potassium is 4s1, 5s1, 6s1, 7s1. Everything in here is s2, so beryllium is 2s2, magnesium is 3s2, and so on all the way down. D orbitals are being filled. If you remember the problem we just did with element number 21, scandium had a configuration 3, that's a 3, D1, that's the 3D1 electron right here, 3D2, 3, 4, 5, 6, all the way over to 3D10. So the D electrons are being filled here. The P's are being filled over here. So boron was P1. Well, so is aluminum, but aluminum, instead of being 2P1, aluminum, this particular electron is going to be 3P1, and so on. The only oddball up here is helium, but we know why helium is over here, because it is a noble gas. So the other thing is, everything over here, all these atoms that are over here, that are, I'm kind of highlighting right now, are noble gases. The reason is they have full outer shells. Helium is 1s2. Its outer shell is full, it's stable. Neon is 1s2, 2s2, 2p6. Well, where's the valence shell for this atom? We know that the neon is over here, and neon should have 8 valence electrons. It comes out that the valence shell is always the outermost s and p orbitals. And if you add up the outermost s and p, 2 plus 6 gets you 8 valence electrons. So this is a pretty astounding pattern that we get from the periodic table, and it's one of the last patterns that we're going to see, that each type of orbital is filled in only one particular place, one region on the periodic table, with the exception of helium. So it's a pretty amazing pattern. So right now, this lecture, we're at 46 minutes, and we still have more to cover in Chapter 6. But I want to finish this particular lecture right now, and then start a second lecture that covers the last bit, just so these lectures aren't incredibly long. So what did we learn today? We learned that matter can act like a wave. Matter can act like a wave, and in fact, the wavelength of matter is equal to h over mv. This is the famous de Broglie wavelength. And from this, we get all kinds of technology: neutron diffraction, electron microscopes, etc. It's an amazing thing. We learned that we can either find the position of a particle, or we can find its momentum, but we can't know one or the other. This is equal to h over 4 pi. This was the uncertainty principle. We learned that Schrodinger comes up with a wave function to describe the probability. Can I write probability? Probability. I can't, hold on a minute. Probability, I wrote it. Schrodinger has a wave function which describes the probability of finding an electron, right? So from this idea of the wave function, we come up with orbitals. And we know there are lots of different types of orbitals, and they're all very strange. If we know the different orbitals that an atom has, we eventually know the electron config. We can find out where exactly all these electrons are. And that is a wrap-up of this particular lecture. Have a great day. I'm going to post the second lecture probably later today. All right? Have a good one. Wait, I have to turn off the video. Okay. Have a good one.